Hello everyone, hopefully welcome back to another Leetcode problem. Today we're going to be doing number 1498. The title is Number of Subsequences that Satisfy the Given Sum Condition. So the first thing about this problem is subsequence is kind of a misleading word, and I think they actually mean subset. A subset is sort of any combination of the sort of elements in the set. A sequence kind of implies that they're in order. And maybe actually that's a hint to the problem that we can sort of analyze maybe a little bit later, but starting with the definition of the problem, we're given an array of integers and an integer target, and we have to return all subsets, non-empty subsets of our array, such that the max and the min, the sum of the max and the min, is less than or equal to our target, which we're given. So we have some examples, right? 3, 5, 6, and 7. If this is our input and our target's 9, we can construct these subsets that satisfy that condition. So there's sort of, whenever you read a problem, whenever someone tells you a problem, you should be looking for hints. Like maybe this is a hint. Turns out it's not, but maybe it was. I was thinking it was at first. This format, why do they say 63 minus 2? Why don't they just like tell you 61? This format, why do they say 2 to the 7th, right? So let's sort of jump into what these hints kind of mean. So one key part with this problem is they said count the number of subsets. They did not say return the subsets. They did not say anything other than count the number. Tell me the number. And in general, when you hear tell me the number, it's going to mean you're doing some sort of mathematical manipulation. And just a little bit of backstory or back sort of material, the number of subsets of any array is 2 to the n. That's the power set, right? I've enumerated them all here, and they specifically said, non-empty arrays, so we cross out the empty array, empty set, and we're left with 2n to the minus 1 is our form. So we're going to be dealing with sizes of the form 2n minus 1 basically for the rest of the problem, and that just comes from how we compute the power set given an array. So one thing about this problem as well is if you think about it for a bit, you think about the subsets, you'll realize that order doesn't matter. So the array that they give you, you don't need to preserve the order in it. And in general, whenever order doesn't matter, which can be sometimes tricky to figure out, but sometimes not, and in this case, it's very clear that it doesn't because the subset is just any numbers put in, and the max and the min can be anywhere in there. It doesn't change where the max and min are. It doesn't change our problem. So the first thing you should be thinking of is, can I sort this, and will that help me exploit some sort of structure? And maybe not even sorting, it's can I rearrange this? The first instinct should be sorting though. And it turns out sorting, is going to help us, and I'll sort of walk through that. Let's imagine every subset of our array satisfies the condition. So 63 is what? There's 6. This is of size 6. 2 to the 6 is 64. Subtract 1, we get 63. So there's 63 subsets here. I don't even care to enumerate them all. But let's assume that all of them satisfy the condition. So let's look at this. Let's look at the max and the min, assuming all of them do. The max and the min is 2 and 7, right? Anything less than that is obviously going to satisfy 2 and 6, 2 and 4. But it's not necessarily true that some combination in the middle will satisfy that. So we have to answer the question, how can we determine whether or not there's some subset that doesn't satisfy the condition? Well, we're not going to get any better if we move this pointer, if we imagine we have 2 pointers, why not? Because we assumed all of them satisfy the condition. So what we have to do is we have to say, okay, 63, you either are exactly equal or you're too much. So we need to move this pointer. Okay, so the initial part of the algorithm is going to be, is there some number that I can reach that breaks my assumption? There is. Once we arrive at 6, 6 plus 7 breaks our assumption. So right away we know we need to subtract something from this number. We've overestimated the number of subsets that satisfy our condition. So let's enumerate the power set of 6, 7. 6, 6, 7, 7, and the empty set. Don't care about this. We can see very clearly there is a subset here that satisfies this condition, 6. So right now, if we subtract, right, if we say, okay, we have 63, let's assume all of this set doesn't satisfy the condition. Well, what's the power set of that? Well, we just computed that. It's 2 to the n minus 1, which is 4 minus 1, right? But we can see that we shouldn't be subtracting all 3 of these because one of these satisfies. So we move this pointer over. Does that help us? It does, because now our right pointer is no longer looking at 7. It's 6, and our set of 6 is 6 and the empty set. And we don't care about the empty set. So we can add it back in. So our algorithm, right? Our algorithm is going to be subtracting sets on the assumption that we have all of them, and then adding sets back in when we realize we've overestimated. And you'll move these pointers based on whether or not you can break the condition or reestablish the condition. So let's try another example. We have 5 numbers here, so we have 31 sets, and for I've enumerated them all here, and we can sort of look at that in a bit. So let's try this algorithm again. And sort of the logic behind this again is, let's assume all of them work, 31. Can I find some number in this list that breaks that condition? Well, again, moving this is not going to help us, right? We already know 1 and 6 works. 1 and 4 is absolutely going to work, right? And this is a sorted list, remember. So does it necessarily mean moving this works? No, because that changes our minimum. And we're trying to keep our sum below less than or equal to 8. So it turns out 2 actually does work, but does 3 work? No, it does not. So once again, let's assume all of this doesn't work. Let's subtract 2 to the first minus 1, or 2 to the third minus 1. Okay, and then let's try to reestablish our condition. Move this over. Does this work? Yes, it does. 3 and 4 do work. So we shouldn't have subtracted all these. We need to add back in the rest of these, right? And it turns out a little bit of, code manipulation, some sort of conditions. It turns out that we could just stop here if we're smart and we code it up. We could continue, right? We could add these up and then move this over and move it over again once we sort of realize, and then this can be our terminating condition, etc., etc. But the main idea is sort of this algorithm here. We're done. What does this equal? 21 minus 7 is 24, plus 3 is 27. So let's look at our power set. So I've enumerated all of the sets here. This is our power set minus the sort of empty set. And I've starred the ones that break our condition. 6 plus 6 is 12. 6 plus 3 is 9, 6 plus 4 is 10, and 6 plus 3 is 9. And you can see the rest of them, have the min plus max is less than 8, and 31, minus 4 is also 27. So sort of this algorithm of sort of assuming one thing and subtracting and adding back in, I wouldn't say it's super common, and I actually kind of enjoyed this problem because it was slightly unique, but I wouldn't say it's too rare either, in that usually there's going to be some sort of mathematical manipulation when you're counting something. So here's the code for the problem. It's has some sort of small tricks in it, but for the most part it's sort of the algorithm that I showed in the video. All this code will be on GitHub, so if you want to take a deeper look at it and debug it and what have you, it'll be in the comment link. So thank you for watching, and hopefully it was helpful. And like I said in other videos, I'm going to try to do sort of regular videos, so if you like this, like, subscribe, what have you, and hopefully see you next time.